like I just mentioned, the one that I did for first block, it started up here and it's going to travel down and then compress the spring. In this example, we're going to have it fully compressed, and then it's going to, so that's going to be at state 1. It's going to travel horizontally at state 2, and then state 3 is going to be when it reaches the maximum height. Alrighty. So, in these problems, there's going to be 3 questions that you should ask yourself to help yourself figure out what types of energy are present at each state. Okay. So the first one, now it doesn't matter what order these are in, as long as you ask all 3 of them. So is there a height from the ground? And we're going to assume that the box is not there, and it's actually right here. So this is, like I said, I was trying to work on the figure before class, but it didn't export properly. All right, so that's the spring and the little panel thing, and then I got the box here. So we're going to assume that over here, this is the ground, and the box, trying to get my mouse, the box is going to be launched, and it's going to slide this way, and it's going to travel up the ramp until it reaches a maximum height. So at state 1, all right, Iverson's here. Did Kadeem come in? No. Okay. So at state 1, is there a height from the ground? Now this question is designed to help you figure out, is there U-grav present? So is there any gravitational potential when the box is at state 1? No. It's going to be touching the ground, so there's no height from the ground, so there's no gravitational potential. The second one is going to be, is there a velocity? And this is going to deal with kinetic. So does the object have a velocity the instant right before I launch it? No. So there's no velocity there. Like, this is the instant right before I'm getting ready to launch it. And then lastly, is there a spring that's being compressed or stretched? And that's going to be U elastic. And in this case, yes, there is. So state 1 is when the spring is fully compressed. I'm getting ready to launch it horizontally. All right. So at state 1, I have U elastic. Cool. And then all I have to do is ask those same questions at state 2. So state 2 is when the box is traveling horizontally, like that. Get rid of this. So the spring has now released it and is traveling horizontally in this direction. The first question, is there a height from the ground? No. Does the object have a velocity? Yes, it does. And is there a spring that's being compressed or stretched? And I should have by the object. No. So the only one that is present is going to be kinetic. Any questions so far? All right. And then lastly, at state 3, the box has reached the maximum height. So when something reaches a maximum height, is there a velocity at that point? If something travels upwards and it's reached as high as it can go, it's then going to travel downwards, right? So in that case, there is no velocity at state 3. Is there a height from the ground? Obviously. So we do have ugrav. And is there a spring that's being compressed or stretched? That's not being touched by the object, so no, there's no elastic. So at state 3, in this example, I just have ugrav. Cool. Now, when we talked about energy before, yeah, what's up? In this particular example, yes. But it's not because it's in the middle, it's because when I answered these questions, the only one that was present was kinetic. Like if the object has a velocity, then it will have kinetic energy. If we put a magnet in the spring and made the box metal, could be stretch the spring. Technically, yes, but that would be a different problem. Okay, so when we were talking about energy before, remember that energy is conserved. So all the energy that I start with must equal the amount of energy that I finish with. And throughout this entire procedure simulation, the amount of energy is conserved. There's no friction, there's no air resistance. So nothing is lost. All the energy is conserved. It just changes form. So it's all gravitational here, then it's converted into kinetic, and then it's converted into elastic. And then it keeps going back and forth. So all the energy at state 2, state 1, and state 3. So if, for example, if I knew that the energy at state 1 was 500, I would then understand that the energy at state 2 was 500. And then at state 3, 500. Make sense? Total amount of energy that I start with remains the same throughout the entire process. So knowing that, we can write it like this. Use the black pen. So the total amount of energy at state 1 equals the total amount of energy at state 2. I don't know what that was. And that equals the total amount of energy. Cannot write any letters today. Total amount of energy at state 3. And remember that the total amount of energy at any particular state is just all of these energies added up, right? So it's going to be U elastic plus U grav plus kinetic. Okay. And depending on the state, so if I was talking about the total amount of energy for state 1, it would be U elastic 1, gravitational 1, and kinetic 1. And let me do that in a different color so it can stand out just a little bit more. So if I'm talking about the total amount of energy at state 1, it'll be U elastic at state 1, gravitational at state 1, and kinetic at state 1. That makes sense? So the reason why I get you guys to answer these questions and to figure out what energies are at each state is in order to make your lives a lot easier, instead of having to put this for each one. So this would be elastic 1, grav 1, kinetic 1, 2, 2, and 2, 3, 3, and 3. So all this looks really messy, right? So the reason why I ask you to do the questions is so we don't have to deal with any of this. Because we like to make our lives easy. So the total amount of energy, the only energy that is present at state 1, is elastic. So it's going to be U elastic at state 1. And that's going to be equal to whatever energy is at state 2. That's going to be kinetic energy, state 2, and then U grav, state 2. You're math magicians, not mathematicians. Funny. Okay. Is everybody tracking so far? Any questions? Okay. So when I give you guys a problem like this, I'm going to give you some knowns. So for this example, I'm going to ask you to find the height at state 3 and the velocity at state 2. So that means I would have to give you the mass of the object, and that's going to be some number. I'm going to have to give you gravitational, or the acceleration due to gravity. I have to give you the spring constant. Remember, this is just a lowercase k. And then I have to give you how much the spring is compressed or stretched. So the objective is I need to figure out the height and I need to figure out the velocity. Is this too small? All right, see you, Adrian. Okay. Trinity. You said you honestly don't get what we're doing? That was for Trinity. I don't know if you're responding to Stuart or not. Okay. All right. So since you're lost, maybe going back and watching the live stream again, it might make sense after that. Cool. Because it might be a little piece of information that I mentioned quickly that you may have just zoned out on. Cool. Okay. All right. So what I'm going to do, what I'm going to demonstrate is I'm going to solve algebraically for H3 and for V2, given these variables. Okay. But I'm not going to actually give you any numbers. Okay. I'm going to solve this algebraically. So when you do have example problems to do like this, all you have to do is take that last final equation and just plug in the numbers, like I've done in the past. Okay. So out of each one of these, which one of these can I actually get a number for, assuming that I gave you values? Which one of these equations, U elastic, kinetic, or gravitational, could I potentially solve for if I was given these values? Now, if you guys need a reminder, if you guys don't have these written down, I would highly recommend writing these three equations down. So gravitational potential, the potential due to gravity, is going to be the mass times the acceleration due to gravity times the height. So would I be able to solve that? Do I have mass, gravity, and height in my knowns? No. So I would not be able to solve that one. What about kinetic? Mass, yep. Velocity, no. We're just trying to solve for velocity, so we can't solve that one. So then elastic, do we have spring constant? Yep, got that. And then the displacement of the spring, yes. So this is the one, U elastic, that we're going to use to solve for H3 and V2. And that'll make sense in just a second. Okay. So we're going to use U elastic, and then either one of these, because they're all equal to each other, it doesn't matter which one I start with. So I'm going to set U elastic at state 1 equal to either kinetic at state 2 or gravitational at, that should be state 3. Gravitational state 3, sorry. So does anybody want to make a recommendation? Which one you want to solve for first? Going once, going twice. All right, we're going to solve for the height first. So we're going to solve for H3. So because we can solve the entire thing, this entire portion right here, the U elastic, we're going to put that down here first. So U elastic at state 1 is going to be equal to, and I said we're going to do the height, so that's going to be U grav because that has height in it. So U grav at state 3. Everybody tracking so far? All right. Now I'm going to plug in. So U elastic is just going to be 1/2 times the spring constant times the delta x squared. And then my gravitational potential at state 3 is going to be mass times gravity. And because the height changes throughout the problem, the height of the box goes from, like, it changes height. We have to indicate that it is the height at state 3. So H3. Cool. So my objective is I need to solve for H3. Now this part is really easy. In order to get H3 by itself, I divide both sides. M times G. M times G. And what I end up with is H3 equals my spring constant times delta x divided by 2 mg. And because this is a 1/2 on the numerator, or in the numerator, that would be the same thing as saying, like, just putting the 2 down there and then the 1 up here. Does that make sense? If it doesn't, it's fine. I'm not here to grade you on algebra. This is the final equation to solve for H3. So in order to get the answer, to verify that this is actually the correct one to use, do I have spring constant? Is that given to me? Yes. Do I have how much has been compressed? Yes. Mass and gravity? Yes and yes. So I have values for all 4 of those variables, and all I have to do is plug it in and then get a number. Cool. Now, hopefully everybody's good to go, right? And again, this is being live streamed, so you can go back and rewatch this. And I'm going a little quick because I want to make sure I get everything covered. But if you guys want to, you can ask for clarification afterwards. Cool. All right, so now we need to solve for V2 right here. So I know V2, that's the velocity at state 2, and we're going to use U elastic because we know everything that's in there. So we're going to use this part of the equation there. So it's going to be U elastic equals the kinetic at state 2. So U elastic at state 1 is equal to the kinetic energy at state 2. I'm going to plug in, or I'm going to substitute in what these are. So U elastic is 1/2 times the spring constant times delta x squared. That's equal to 1/2 mv2 squared. Now notice I didn't put a 2 on the mass because the mass doesn't change. All right, so my objective is to solve for V2. So I'll put a box around that. And to get rid of the 1/2, I just multiply by 2 and that cancels out. Multiply by 2, that actually cancels out that one. I divide the whole thing by m. Divide by m. And I'm going to clean this up a bit. So I currently have spring constant times delta x squared all over m. And the m's canceled there. So I've got V2 squared. And again, I'm trying to keep V2 and I don't want the square. So I I take the square root of both sides to get rid of the square. So these two cancel out. And then I square root all of that. So the final equation for this, for the velocity at state 2, is going to be the spring constant delta x squared all over m, and then all into the radical. Cool. Any questions? Again, I apologize for it being really quick, but due to the fact that it is being recorded, hopefully you guys can go back and rewatch that. Remember what? So as with all of my assessments, I'm not here to grade you on algebra. I'm here to make sure that you can look at the equations and look at the situation and figure out which equations to use. And you can write down as many formulas as you want. You just can't write out examples. So anything that I box, like something, I don't know, similar to, I don't know, this, maybe, possibly, you could, I don't know, write down on a, formula sheet, and then you can possibly, I don't know, use it on your assessment. I don't know, just saying. I made that cringy so you guys can listen and pay attention. So these ones I will give you. The other ones if you pay attention to the lectures and you watch the videos, all the ones that I'm like, pointing errors to and stuff, like maybe those are important to write down. I don't know, maybe possibly it could be useful. But if you don't listen to the lectures and you don't pay attention, watch the videos, then you won't know that. So, like I mentioned before, these will be provided, and the other ones you ought to have on your own. And if you do everything properly, the hardest part of all of this is to figure out what types of energy are present for each of the states. So state 3, state 2, state 1. And in the problem statement, I will indicate what direction it's happening. Okay. I will indicate which one is state 1, which one's state 2. I'm going to have different figures for each of the different scenarios. So this would be state 3. This one over here would be state 1. And then I would have the box over here in the middle without the spring being compressed for state 2. And I will have separate figures so they're not all overlaid on the same thing. Make sense? Just to kind of clean it up for you. Any confusion about that? So the hardest thing is to figure out what type of energy is present at each of the states. And that's as simple as reading through these questions, giving it a check mark or an X, depending on which state it is. I would recommend writing it down so you can go back and reference it. But that helps you clean this part up and then setting things equal to each other. So this is state 1. This is state 3. So state 1 is equal to state 3, obviously. And then we're using that to solve for H. And then this one, it was state 1 and state 2. But since they're all equal to each other, it doesn't matter. And I use that to solve for V2. So when you guys go back and watch this video, hopefully it'll click. And I'm going to go ahead and end the live stream so that way it's nice and short so you can go back and